talking about the characteristics of instruments, static characteristics, dynamic characteristics. Those are all very important to describe the ability of the instrument, to produce the correct reading, to reproduce the reading again, how much range it can measure, what kind of frequencies it will be able to support, up to what range you can measure, things like that. The dynamic behavior, what is the lag, how much time it will take to show you the reading, all those stuff we have learned how to tell technically using some terms. Those terms we have learned. I think we have spent a little extra time than we are supposed to, but that's all right as long as you understand it. Okay. Today is all about the error. Okay. Eventually, while taking reading using instruments, errors are bound to happen. Okay, lot of reasons. We wanted to take the correct reading, or rather, we wanted to measure the true value, but there is always some kind of error that creeps in most of the cases, and we take some other reading than what we intended for. So there is something called error that comes. Now today's lecture is all about what are all the sources of error, so that and what are all the remedies for that. If it is possible to reduce, we reduce. If it is possible to rectify, we rectify completely, and then try to do our best. Number two, we will be trying to quantify the error. Okay, this is the error. If I know this is the error, at least I can do some adjustment in the reading and then understand what is the true value. I cannot do this, quantify, I cannot do anything in the measurement to reduce the error. Then at least if I know this is the error, and the case is more, the difficult situation when we have more than one parameter and then try to get the meaningful parameter out of it. For example, a parameter is computed from 2-3 measurements. Power transmitted by a shaft. Power P is given by 2 pi nt by 60. 2 pi by 60 is constant. N is RPM. We take speed measurement. T is torque. We take reading from torque measuring instrument. And out of these two measuring values, we compute power. If speed is having certain error, torque is having certain error, then power will have the compound error. Okay, how to compute the combined errors of the parameters of that sort. If I am only interested in speed, probably the case is a little simple because we need to quantify what is the error. When a parameter is computed from two parameters which are measured from instruments, each of them will have some error, and how they exhibit themselves in a formula, whether it is in denominator, whether it is in numerator, when parameters are getting added, when parameters are getting subtracted, how is their interaction? Okay. All those things we are planning to learn today. If at all some spillover is there, next class in few minutes of lecture. Okay, that's the subject matter we are going to see. Now, sources of error. The first thing, what is sources of error? Primary sources of error, secondary sources of error. That is a theoretical classification. We are not too much worried about. Okay. Why I have to learn the sources of error? This, I think, in the first class I have explained why, in fact, we have to learn the instrumentation at all. That's because mainly these three reasons. Suppose if I am a designer, I am designing an instrument. If I know what are all the sources of error for that particular instrument, I can take care that error is avoided in my instrument during the design stage, or if it is not possible to avoid, at least I can minimize the effect of that error in that instrument. Okay. While designing stage, if I am a designer of that particular instrument. No, I am not a designer, I am a user in a particular company. I am now buying an instrument. If I am buying an instrument, if I know what are all the sources of error and the remedial action well in advance, I will be able to know, I will be able to select the right instrument which will get affected less by the parameters that my environment has in my company. For example, I am working in a Salem steel plant. It's very, most of the places in Salem steel plant will be very far because there is a steel plant and things are getting rolled, there is a furnace, or you are working in a foundry. most of the place it will be hard. The sensor that you are trying to buy, if it is very sensitive to the temperature, ambient temperature, and the sensor is calibrated at the standard temperature of, let's say, 25 degrees Celsius or 27 degrees Celsius, you take it to your factory where the temperature is 32, 33 degrees Celsius, naturally you will not be able to get the correct reading all the time from the instrument. Morning one reading, afternoon it will do some reading for the same input. It will give. It will produce error, reading with more error. Okay. So if I am an engineer selecting the instrument, I will be able to select the better instrument which will have less variation with respect to temperature, so that I will be able to reduce the error in the reading. Now I have already selected, I have joined a company, already there are some instruments. If I have enough knowledge about the error, I know this instrument will produce this much error because of this parameter. If I know already, I can quantify that error and then correct that in the reading. If it is positive error, I can subtract that value, so much error value from the reading, I get more or less true value. If it is on the negative side, I add the error value to the reading, I get the more or less true value. So I can try to reduce the error as much as possible. If I know the sources of error and the knowledge about that topic, I'll be able to do these things. Okay, right. The classification of errors comes like this. The error can come from only 4 things, because you instrument, this environment, what more is there? The observer, isn't it? And additionally, loading effect. I told you last class we will be talking more about the loading effect this class, isn't it? So loading effect, we will be talking about the interaction between the parameter and the instrument. So only there are 4 things. Let's say I am trying to measure temperature in the lab. Okay, temperature is the one, instrument is second, I am observer, I am the person who is performing that exercise, whatever, the experiment or whatever. I am third, and fourth is in a particular environment I am doing this. So error can come from any one of these 4 only. There is no fifth element. So it can be from the instrument itself there is an error. Environment, loading effect is basically because of the interaction between the parameter and the instrument, and it is the experimenter. It is an experimenter, the person who is performing this exercise. Error due to instrument may be due to various reasons. Every instrument is designed and manufactured. In the design stage itself, designer would have missed certain aspect. Because of that, my error may come. For example, he might have chosen a material which is non-homogeneous, okay, in composition, and he might have chosen that as a element for measuring temperature. So let's say because of temperature, the 2 strips of metal will bend, and the bending is proportional to the temperature. That's the working principle of certain temperature measuring devices. And in that, if the material composition is not uniform, you expect the metal strip to bend to a certain angle, but actually it will bend a different angle. That's because of design error. Design stage itself, the person has made a problem. Of course, there is a problem with the material also. I have given the correct composition, but during manufacturing, the correct composition is not always ensured, and then come with the wrong composition. Naturally, my manufacturing defect will be there. Again, it will have wrong reading. The error may be introduced because of that. It may be due to poor design. It may be due to assembly. Okay, especially most of the metrological instruments and other instruments, during assembly, if it is not properly assembled. For example, you have a Borden tube pressure gauge. There is a dial that you have to fix it onto the gauge. If the dial is not properly rotated and kept, the needle is supposed to read 0. It will not read 0. During assembly, if there is a small mismatch, it may read any sub-zero reading or 1 graduation, 2 graduation on the positive side, it will read. So during assembly also that kind of problems can happen. Error in the graduating scale can happen, non-homogeneity of the material, non-linearity of the material, all this can result in an error in the reading. Okay. A typical example is backlash to the screw gauge or dial gauge. The backlash is something like this. You know what is meant by backlash? You take a screw gauge, or if you don't know a screw gauge, you simply take a screw, bolt and nut arrangement. You keep the nut, bolt and take the nut, you rotate it in one direction. The nut keeps on moving, isn't it? Inside the nut. and suddenly you reverse the direction, you start rotating in the reverse direction, the nut will not start moving towards the opposite direction immediately. For a certain amount of movement, small movement, not very great, for a certain amount of reverse movement, the nut won't move in the opposite direction, because there will be a gap in the thread. For the thread to reach from here to here, this much gap, there won't be movement in the opposite direction. Okay, this plane, this gap for which there is no reverse movement is called backlash. This gap is called backlash. Typical problem in most of the screw type of instruments, wherever, like typical example is micrometers. Okay, so all these problems will be there. Non-linearity problem is, material will behave linear only in certain range. Most of the material will become non-linear beyond that range. Okay, so by nature all are non-linear. So we will be using the instrument up to the linear range. By mistake, if you have chosen little longer range, or you have used, the manufacturer would have told, for example, thermocouple, particular type of thermocouple, they will say this thermocouple you can use only from minus 40 degrees Celsius to, let's say, 300 degrees Celsius. If you put that thermocouple in 400 degrees Celsius, still some reading will come. There is no guarantee that there is linearity and the correct reading is displayed. There is no guarantee about the correctness of the reading. So if you go beyond the temperature that you are supposed to measure, not only temperature, anything from that matter, beyond certain range they become non-linear. So if you go to non-linear region, then error will be produced. Reading will come, even out of the way if you use, reading will come from the instrument. It may get damaged, that's a different issue. Even without damage, some instruments will produce reading, but that reading, no guarantee that will be the correct reading. That's because of non-linearity of the instrument. Like that, you can keep on giving examples for various types of error in the instrument itself. Okay. Anyway, that is more or less predictable, and also that's very fixed. So we don't worry too much about that. If an instrument is having problem, that has a problem. We will be able to easily identify and do some remedial action for that. The more dangerous sources of error comes from the environment. What is meant by environment? The temperature, pressure, humidity, the high power lines that we are going. 20 years back, there is no sources of error, something called radiation from the cell phones. The only RF signal that's available in air was All India Radio, AIR. Only that is transmitting some RF waves. Today, you see how many electromagnetic waves that every one of you carrying a source of error. Every one of you having a cell phone which is transmitting some waves, and that is disturbing the instrument, which is producing electric signal from physical parameter. That gets disturbed when you take cell phone very close to that phone. You take a reading with respect to the power lines like that, high power lines. Inside the junction box, there are 240 volt, 50 hertz Tamil Nadu electricity board current is flowing, and you take near to that, there will be an EMF set up around that. Any current carrying conductor, there will be EMF set around that. You take a reading closer to that EMF, then there is all possibility that your sensor wires or cables that is transmitting the peak signal get disturbed by that electromagnetic force. You get a wrong reading. It can introduce an error. So temperature, pressure, humidity, wind velocity, the wind that is going across the room, the AC power lines, acceleration due to gravity, RF waves, electromagnetic waves, all that forms the environment. The error can be from any one of this. The error can come from any one of this. We'll talk about how to solve some of the commonly occurring sources of error in a couple of minutes. Before that, the loading effect. Loading effect is defined as, what is loading effect? During the act of measurement, some amount of energy is hidden away by the instrument, is taken by the instrument for the purpose of measurement. This effect is called loading effect. Last class we have seen, isn't it? Last class we have seen. Now, let's take an example. Alan, suppose I give you a sponge. sponge. You know, for wiping or washing the grinder, the sponge your mom would have used, isn't it? Big sponge. I want the exact measurement using micrometer or vernier caliper. I give you a vernier caliper and then ask you to measure. What will you do? Yeah, dimension. I just want the width of the sponge.
Without compressing it.
You know, have you ever used vernier caliper? When will you get correct reading? You try to push. There will be a moving scale on a fixed scale, and you try to push as much as possible on a metallic rod, probably, to find out the diameter of the rod or the slab thickness. You press as much as possible and lock it and then take the reading, isn't it? That is how we take reading. In sponge, how will you take such a reading? If you press for the purpose of getting exact measurement, the sponge is getting reduced. The thickness of the sponge is getting reduced. Suppose you don't press, you don't get the exact reading. Okay, so that's a problem there. That's a problem there. For the purpose of measurement, if you slightly apply pressure, the thickness of the sponge is getting reduced. The thickness of the sponge is getting reduced. And that alters the thickness itself or width itself. So that's loading effect. The reduction in the width for the purpose of measuring the width is loading effect. Right? Let's say vernier caliper, micrometer, whatever it is. We wanted to measure temperature. Most of you now have started using thermometer in the hot bath. You have a thermometer, put it inside the hot bath. It's a hot bulb thermometer, right? So liquid bulb. So what is there inside the bulb is a liquid. The moment you put inside the liquid, what happens? The heat transfer takes place from the hot bath or hot water to the thermometric fluid, and thermometric fluid expands. Thermometric fluid expands, and there is only a thin tube. Because of that, the thin tube column level rises. Isn't it? Do you think the temperature will be same before inserting the temperature and after inserting the temperature? After inserting the thermometer? No. I wanted to measure the actual temperature. I am inserting what? Thermometer. Just because I inserted a thermometer, some amount of temperature is dropped down. Some amount of heat is absorbed and temperature drops down. This drop in temperature, because of thermometer which I have inserted for the purpose of measurement, is loading. Flow measurement. Have you done fluid mechanics laboratory? Okay, you might have used abstraction type flow meters like orifice meter, venturi meter, flow nozzles, or even turbine meter, things like that. A lot of abstraction meters. For all of them, what we do? We have a particular diameter of pipe. Jason, we have a particular diameter of pipe, and then we put orifice. Orifice means what? The abstraction plate with a smaller hole than the diameter of the pipe. It may be circular in shape, it may be semicircular in shape. A lot of varieties are there on, I think some girls would have designed. A lot of designs are there in orifice meter. Okay, there's a small hole that is good enough, but then plenty of designs are available if you go more into that. Some of such designs I have given in my book. Those who are interested can go and refer. It's available in the library. So, lot of designs are there. Basically, we wanted to disturb the flow pattern. That means obstruct the flow pattern. Amount of flow. What is the purpose? I want to know what is the amount of fluid that is flowing. For that, what I do? I create a pressure difference. Upstream pressure, downstream pressure I measure. Then the pressure difference and other formula that I have, I find out what is either velocity or Q, the discharge volumetric flow rate, and then I find out that. For the purpose of measurement, I am disturbing the flow. Will the flow pattern will be same without orifice meter and with orifice meter? It will be very much different. I have already disturbed. But then, for the purpose of measurement, I don't have any other go in that particular instrument. So, we call that effect as loading effect. The amount of disturbance made is loading effect. I'm loading. Of course, if you are from electrical background, you can easily appreciate this. Even otherwise, you can understand this. I want to measure voltmeter, current meter. I want to measure voltage or current, not measure voltmeter. I want to measure voltage or current. So what do? I take a multimeter, put it in voltage range, two probes, connect parallelly to the source where I wanted to measure the voltage. Now, I wanted to measure the voltage. For that, what I am doing is I am connecting that to a circuit so that the current will flow and there will be a voltage. There is a voltage drop because of that resistance. There will be a resistance, there will be a voltage drop. That is actually measured by the multimeter and shown in the reading. And then the circuit comes and then get closed. Okay. For the purpose of measurement, actual voltage is taken, passed through a resistor, voltage drop is computed, and from the voltage drop, the multimeter understands what is the voltage at the source, and it displays there. Some amount of drop is there. The voltage is no more the actual voltage. There is a drop in voltage. It is disturbed. The voltage is disturbed, no more the same voltage. The amount of disturbance that it causes is actually a loading. Go on giving like that. Lot of examples. I think the last one may be familiar one to you. You have a mechanical tachometer. Of course, optical tachometer is there. There is no loading effect in optical tachometer. Okay. There is no loading effect. Mechanical tachometer. In mechanical tachometer, what we do, we have a DC generator inside the instrument. We have a shaft which can be rotated with a conical end. We take the conical end, go to the shaft. There will be a conical dent. We press the tachometer in the conical dent. Then you have to press a lot. Then only the actual speed of the shaft transmitted to the shaft in the tachometer. When both of them are rotating at the same speed, there is a tacho generator which generates voltage, and that voltage is calibrated in terms of RPM, so you get the reading in the RPM. So while reading, you can pick the RPM. Suppose you don't press properly, there will be slip, and the rotation of the shaft is not fully transmitted to this, there will be an error. So to avoid that error, what you do? You press it with full force. Okay, full. A shaft is rotating. You apply something against that full force. Do you think the shaft will rotate at the same RPM? You apply torque to a rotating motor, 2 by 80 by 60. Power remains constant. You apply torque to it. Speed will get reduced. Speed will get reduced. It is no more the actual RPM that it was rotating. Maybe 1 RPM less, 2 RPM less, 3 RPM less. It is not the same RPM. As simple as that. There is error produced. This error is due to loading. I am loading the system for the purpose of measurement. Okay? Loading means not putting weight in a mechanical sense. In a conceptual way, I am putting extra load on the system. Okay? It's like workload, or work pressure, something like that. I am putting extra load onto the system for the purpose of measurement. That's loading. Errors due to experimenter, I told, we are also part of the measurement, isn't it? We are taking reading. Sometimes the scale may be here. Okay, the needle will be here, scale will be on the back. If I am reading from here like this, I will be reading more than the actual value. Suppose gauge is here, normally this is the case. Gauge will be here, needle will be here, and on back side there will be a scale. Normally, we don't bend down and then take the reading. We are normally okay, slight bend and yeah, this is the reading. So we tend to do this while taking reading. So parallax error is bound to happen taking measurement. Erroneous observation. And then some misuse of instrument. That's because of lack of knowledge about that instrument. I don't know about the range, outside the range I use. I'm not supposed to connect, I want to measure voltage. If I connect it in series, I cannot measure the voltage. For voltage, you have to measure the instrument in parallel. Like that. You are not supposed to do, but then you do that because of lack of knowledge about that instrument, misuse of instrument. So that also can introduce error in the measurement. These are all sources of that. Any questions on that? We can talk more on that, but considering time, I have encapsulated into half an hour back. Any questions? Mahesh is happy. Oh God, 2 minutes this fellow stopped the talking. What Mahesh? I see a lot of happiness on your face the moment I stopped talking. Good. Any questions?
How does reading of the computer?
Yeah. Suppose I am taking temperature reading. Normally in the lab you see the readings are oscillating. That's because the fan is on and wind velocity will be there. We are about to take the temperature. You put a sensor. The sensor is supposed to experience the same temperature as the medium. Then only we will be able to measure the actual temperature. Suppose if wind velocity comes and cools the thermocouple closer to the hot junction, then the temperature actually sensed will not be equal to the temperature sensed by the sensor. The medium of the temperature and the sensed temperature will not be same. So if the wind velocity is there, it gets affected. Not all measurements. These are all some of the, some instruments will be affected by some parameters. Like humidity. Humidity, for example, we have a capacitance-based level sensor, isn't it? Capacitance-based level sensor. The humidity will affect the capacitance value a lot. Like that, certain parameters will affect certain measurement. And no, sorry. Any doubt? When the class gets over? Is that the doubt? What sir? Only it is 10:30. So it goes up to 10:40. 10 minutes. He is thinking 10 more minutes I have to sit. Acting as if I am listening. Very tough job. No? Act continuously. Sai? Nice job. Doesn't talk anything. Always want to smile. That's all. Okay. Methods of reducing error source. Let's say we understood these are all the sources of error. Now how to reduce them? The first one is, suppose you have, in the olden days, most of the instruments are all the pointer based. Okay, there is the friction, there is a bearing on which a small bearing is not big one that you see on the vehicles. In the instrument there will be a small bearing for rotating the needle, isn't it? The pointer scale. There will be a shaft, there will be bearings, and the shaft will be rotating. Because of that, the reading is shown by the pointer on the graduated scale. And if there is a friction in the bearing, and of course there will be friction, but if the friction is more, then your dead zone will be more, or it will not move properly. You need loading effect will be more, or the error will be introduced. All that. How to reduce the friction in the bearings? The frictional bearing force, the moment, is given by the weight times the friction coefficient. It's actually mu. I put m because while typing I was finding mu, but then due to lack of time I just typed m. It's actually mu. The correct formula is mu. And r is the radius of the journal. Bearing. So you have weight, you have coefficient of friction, and then you have radius. One thing, you can use a smaller bearing that will reduce the friction by reducing the R. M is the coefficient of friction. You can use lower coefficient of friction so that the friction is less, or you can reduce the mass of the entire setup. Next time when you go to lab, once you enter, you turn right side, there will be a hydraulic trainer kit. You go and see there will be a pressure gauge which is filled with some liquid. Pressure gauge with a glass, graduated scale, pointer, everything. It's filled with a liquid. Why they have poured water inside the gauge and it is made to float? Normally the swimming pool, you might have realized, your weight is less when you are in the water, isn't it? Right? You can easily carry a person inside the water, whereas outside it is difficult to carry. You realize, right? So if you make somebody to float on the liquid, the weight gets reduced. So that's the technique by which your weight is reduced. We could not reduce the mass. Weight, we could not reduce the mass. So much big has to be there, so much width has to be there, this metal has to be used. So that and all is decided by other design consideration. But still I have to reduce the weight. One way is use the liquid so that the weight is seemingly less for the bearing. And then of course go to the friction using lubricant or any other possible material itself with the lower coefficient of material that you can use. And radius itself you can use. So bearing friction is decided by 3 parameters. Try to reduce any combination of 3 or all parameters. So friction is less. Number 2. Backlash. We said backlash is a big problem. It can be backlash means this is for an illustration for easy understanding. But normally this backlash you can see in all your pointer scales. The pointer scales, Alan, pointer scales. Huh? What is it? What is pointer scale? Your attention should be here. Because twice I have noticed you are not mentally here. So you have multiple gears. You have one big gear, you have another small gear, and finally, maybe during pressure measurement, you will be able to understand. Of course. This is a cartoon representing 2 gears. Of course, it's not a diagram. There are 2 gears, and what happens to this pinion, the last pinion, the pointer is attached. This is a graduated scale. Okay. So now here, while rotating, for some movement in the reversal direction, I already in the last measurement after I took, the needle has come back to 0, and now it is in the 0 position. Let's say this is 0 position. 0. It has rotated. Now it has to start rotating in the reverse direction. But backlash, for a certain amount of movement of this gear won't rotate because of backlash. Okay. But I want it to always rotate, however small motion it is. For some movement of this gear, if this gear is not moving, there is another term for that. Even this will result in the dead zone. Because of some input parameter for which there is a change in whatever it is. Finally, it is rotating, but this pinion is not rotating. Because of the backlash, this will result in dead zone. Okay. As a gauge, it is dead zone. When you analyze, it will be a backlash problem inside. So always, whenever there is a measurement, if it rotates, I want this gear to rotate. Okay. Any direction for that matter. It is clockwise, anti-clockwise. I don't want any motion to get lost because of backlash. That's the problem that we have. So now, what we do is, this is a circular toothed device. It is applicable for linear also. Only thing it is in the circular form, it is in the linear form. It is easy to understand the linear form, so I have put it in the linear form. So what I have one gear that I have attached to a spring, to a body of the gauge. The body is fixed, like wall. I attach a spring and connection. Spring 2, this is free to rotate. This is operated by the physical parameter. Gear 2 is operated by physical parameter. Gear 1 is connected to the pointer. Any movement in gear 2, I want there should be a movement in gear 1. Or vice versa. Any movement in gear 1, I want there should be a corresponding movement in gear 2. Is it alright? Okay? Now let's say, just because I put a light spring, it's a light spring, that's very important. It should not be very heavy spring, very light spring. That's why the watches as well as in the gauges, you will see there will be a spiral spring, very thin spiral spring that is attached. One end is attached to the body, other end is attached to the pointer, which is rotating, or the gear which is rotating. Okay, that's because always that spring will keep this is in contact. This gear 1 is always pulled against the gear 2. This will be in contact. Okay, see, there is no gap between two surfaces. If gear, that light spring is not there, then you will not see that surfaces are touching each other. That will be floating somewhere and results in backlash. Now, if you move the gear 2 towards left, because it is already touching the surface, gear 1 will also move towards left. No motion is lost. No motion is lost. Suppose the gear 2 is moving towards right, this will move right. Actually, there is a gap on the right hand side. So, gear 2 will initially move, but because of the light spring is pulling it towards the other direction, gear 1 also will move to the same extent without any loss of motion. Whatever is the motion that's happening in gear 2, same amount of motion will be there in gear 1 as well. Is that clear? Okay. So backlash is completely avoided by using a light spring. But light spring will introduce another problem, a loading effect, because in order to show reading, you have to overcome the light spring force. That's another problem. That's why it is make it as light as possible, but do this function. Okay. Non-linearity and non-homogeneity. Whatever it is. Non-linearity problem, of course, you have to be very careful that you should use in the linear region itself. That's the best solution. There are a few remedial actions that you can take. If there are undesired non-linearity effect. For example, I have a metallic strip. I do not want it to bend while measuring. Okay, but due to the ambient temperature, it is bending slightly in one direction. Instead of making the strip with one material, I will use two materials. What is that? One will have positive temperature coefficient so that it will try to bend downwards. The other half, on top half, I will put negative temperature coefficient so that due to temperature it will bend in the reverse direction. Net effect, it will not bend. Almost I will match the temperature coefficient on both negative and positive equal so that the material will not bend because of temperature. So I will try to use the opposite effect and then try to compensate for it. This kind of technique we can do. Very rare, not in all measurements you will be able to do. Very rarely, if this kind of ideas may be used to eradicate or reduce the error because of non-linearity or non-homogeneity. Non-homogeneity is mostly to do with manufacturing process. For example, I want tungsten carbide or tungsten material. Okay, we have to take tungsten, the purest form, pour it into the die. There should not be any dirt. There should not be any extra element coming in. It should be homogeneously made so that the tungsten tip, for example, if I want the tungsten tip, I will get. Non-homogeneity, how it comes into play? Suppose I want tungsten carbide. So in tungsten, we will put carbon and then develop tungsten carbide. There will be a stirring process while melting, and if it is not properly stirred, the manufacturing process defect. In some places the carbon content will be little extra, in some process the carbon content will be little less. So the carbon content where it is more will have more hardness and more brittle, and less carbon area will have less of those effects and things like that. Very minor difference would be there according to the carbon content, but still the non-homogeneity is because of mostly manufacturing process. So that you have to be very put tight, stringent rule on the quality and then check the manufacturing process. And nothing big really can be done on like a counter effect of those effects. Temperature is also opposite effect that I have explained. Yeah, with the humidity we will stop. Because few more slides are there, we will not be able to cover anyway this class. Humidity alone. I was working in telephone manufacturing company. Did I tell you? Yeah. We used to get some complaints. 20 years back, if you have used, you must be small kids those days. Even 10 years back, if you happen to use the normal telephones, in rainy season, some of the telephones won't work. Rainy season, some of the telephones won't work, or it will create some problem. It will create some noise while talking, or some sound will come. So some issues during rainy days. Summer it works perfectly well, no problem. We took those phones and then investigated and then found that's because of the flux that is used while soldering process creates all that problem. The flux that is used creates all that problem. The flux material is used to lower the melting point of the lead while soldering. So if you use lead, it's easy to solder. So if you use flux during the soldering process. The flux is hydroscopic material. Hydroscopic means what? Yeah, it will try to absorb water. So after soldering, some residual flux will be there on the PCB and we carelessly left on the PCB itself because it is not going to do any harm. You thinking that it is not going to do any harm. So there will be PCB. PCB means printed circuit board. The track will be going close enough. The tracks will be going close enough. Of course, there will be a closure. The copper tracks will not be exposed to atmosphere. There will be a coating that completely protects. But sometimes if the coating is not good enough and flux is overhead, what happens? The track 1 and track 2, above which there is a thin layer of flux, during winter season absorbs moisture and it will have good amount of water to conduct between this track and this track. So this will have two tracks either will be connected, resulting in short circuit, or creating some capacitance effect, creating some noise while you are talking. So basically when we investigated, all this problem comes because of the flux which is not cleaned properly after the soldering process. So we started cleaning that. We take a brush. Typically we use the toothbrush, but there are special brush available. You take the brush, put it in alcohol, wet it in alcohol. With the alcohol you clean the PCB board after soldering. All the flux material will dry it in the fan for just 10 seconds to 20 seconds. The alcohol will evaporate and then PCB board will go. Or you just send it through a heater in the conveyor. In the process it gets evaporated and then you get PCB formed. The problem is because of humidity. The humidity in the air that gets absorbed by these electronic circuits and that created a problem. This was initial days of development. Nowadays, no instrument gives trouble because of humidity. But if something is not taken care like that, it will result in problem in the instrument. Okay, it will give erroneous reading. You will not know because of what. So you should be careful about the material that you use, whether it is hygroscopy, and then humidity can cause a problem to that. Okay. We stop here.